It's our pleasure to introduce you to our project MaLePoM, which stands for Machine Learning for Pollution Monitoring. Let's start with the problem statement. We are focused on NO emissions, in particular NO2 emissions, which currently rely heavily on inventories. Inventories has two main problems. The first one is they are temporally fixed in a very long time scale, usually months or years, and moreover they cannot capture slight variations, for example rush hour for the traffic or season specific activities like burning crops. Therefore, our objectives are to identify suitable proxy data to estimate NO2 emissions, gather them and create a unique and integrated datasets that group all the proxy data. And with this unique dataset, we will build and train a machine learning model, which should be able to capture both temporal and spatial variability with a high resolution and globally for the NO2 emissions. The project is divided in 6 main work packages. We are almost completed the first 2 of them, which is the dataset creation. We select different datasets from different sources. We are doing the data engineering, so we are selecting the best features and tuning every parameters to define the better datasets as possible. And we also started to create the machine learning model, testing some baseline models. In the next months, we will also, of course, gather the results, create the documentation, and disseminate them. Today we will going to explain you in more details the first 3 work packages, starting from the dataset creation, which is the selection of the proxy data and the integration. And in particular, we have one main source, which is Wikio, the data and information access services provided by Copernicus, that contains a lot of environmental data and datasets, but we use also other sources such as here for the traffic data or Corinne for the land cover data. We have basically 2 types of data. The first one are spatial proxies, which include basically the land use, the land cover data, and the human settlements related data. Then we have the temporal proxies. In particular, we have traffic data, meteorological data, and pollution concentrations. Now for the data engineering part, I leave the stage to Paolo.
Thank you. The second step of our workflow is the data engineering, where we take all the proxy data and we put them together to create the big data set we will use in our model. Our data will be collected in a grid of 0.25 degree. This, Luca, can you go on the next slide?
Yeah.
Thank you. Our data will cover the Central Europe area, and for the time we decide to use the May 2019, and this time frame was decided because the tutor gave us the data for the target variable for this period. The first data set we'll talk about is the land-related data. Here we have 2 features. The first is the human fraction, that basically is the part of the soil who is covered by urban buildings. And the second is the average height, which is the average height of the buildings in this area. And how we can see from the correlation metrics, these 2 variables are very correlated with our emissions. So these 2 variables are very useful for our model. Then we have the weather dataset. Here we have a lot of features like wind, cloud, humidity, and temperature. But all these features have a very low correlation with our target variable. And also, if you use them for a baseline model, we get a very bad performance. After some analysis, we decide to shift the data forward of 9 hours. And doing that, we get an high correlation for temperature and humidity. And also we get a better performance in our baseline model. And so these shifted features will be the one we will use in our final model. And now I leave the stage to Vidur.
Thank you, Paolo. So another interesting data set that we look at is the traffic data. So as Luca said, we get traffic data from here, Traffic API, which allows you to access real-time traffic conditions and query them using an API. So we query the API at regular intervals to compile a database of traffic data and then perform analysis using that data. So this plot here shows the diurnal trend of traffic for two sites. So the orange line is for Milan city and the blue line is for a rural site in Italy. So from this, we can see that there's a clear diurnal pattern in traffic, which is what we would expect. And there's two peaks, one in the morning and one in the evening, which likely correspond to rush hour traffic. So this is promising because highlighting the finer temporal variations in the emissions is one of the aims. And we hope that traffic data will be useful for that purpose. Luca next. Yeah, so this is the area for which we query the traffic data using the API. So it's Northwest Italy or Southeast France, that area. And so we see that for different hours, the traffic conditions vary significantly and that there are some trends that we would expect that are visible. So for example, urban areas naturally show much higher traffic density, and hours like 8 a.m. in the morning, which is the top right graph here, again, the traffic density is higher at that time due to rush hour traffic. So then we also compare the traffic density that we get from the here API to the emissions data that we already have. So we do this comparison for the diurnal cycle. So for using the hourly traffic data and the hourly emissions for the month of May 2019. So the emissions data is for the month of May 2019, but the traffic data, since it's only available in real time, it's actually for July 2021. But despite that, we see that the diurnal pattern matches pretty well for the two data sets. So again, this is promising as a good proxy for the temporal variation in emissions, and we hope to use this as one of the proxy data sets in our final model. So another data set that we consider is the concentrations of various species in the atmosphere. So our aim is to look at predict NO2 emissions. So for that, we also look at species concentrations in the atmosphere, and we look at these 5 species in particular. So carbon monoxide, NO2, NO, ozone, and water vapor. And the one at the bottom is the emissions profile, which we have as the final data set on which we're training our model. So we see that all 5 of these species have a clear pattern or a diurnal or temporal pattern, but none of them necessarily matches with the emissions profile that we have. So to account for this, we would need some sort of time series analysis technique and pre-processing of the concentration data in order to be able to use this to actually correlate with the emissions that we're trying to predict. Now handing over to Nicolo, who will talk more about the machine learning aspects.
Thank you very much, Vidur. So now we're starting the predictive phase where we're gonna tackle the problem from the machine learning point of view. And basically our challenge involves a regression problem where we must estimate the level of A pollution given a set of features. Features are input variable basically to give to the model. And basically what we expect is an estimate, a number. So basically a number. And then we decided to divide our approach from first select some sort of set of models, some baselines model, which provide not very good result, but gives an idea in order to test the features. So now we are testing our features, so creating, modifying variables in order to get a suitable set of features. And then once we got this, we can test different models in order to get a very, very accurate prediction. So feature selections is basically the process of reducing the number of variables. So select a subset of all the variables we got in order to maximize the accuracy of the model. And we can do this by some statistical analysis, for example, by matching variances and correlations among inputs and outputs and so on. And also by using some embedded machine learning techniques. For example, there are techniques which builds a model trying to predict, but it's not a matter of prediction. It's just a matter of what kind of internal ranking does this model to the inputs variable, and we use that to select the best set of features. And once we got that, we start to analyze this model. And so we start from the baseline models. Next slide, yeah. And basically, the baseline model we are using right now to test features are linear regression, decision trees, and sample methods, which basically the key points here is that they must be very, very fast to train and predict, because it's not important to get an accurate prediction, but it's more important to have an idea of how well our features perform in a model. And then by doing this, once we got we will have a good set of features, we then go to the most state-of-the-art approaches, which by looking at the literature, online literature, we see that random forest and support vector regression are two types of algorithms which basically are exploit a regression model in order to get also non-linear variability of the input. And of course, we're going to tackle the deep learning approach. So the recurrent neural networks, long short-term memory are just a type of recurrent neural networks, which are an architecture able to exploit the time correlation between data. So we got time correlation, and of course, provide a very, very good prediction. So this is what we are going to do now, from now on until the end. And thank you very much for your attention.